This is week 4, the second hour. We will continue our discussion about data preprocessing. The second step of data preprocessing after we discussed data cleaning is data integration. And data integration means that we do combine data that is coming from different sources. And we combine them together so that they will become a coherent store. So they make sense together. They look like they are coming from the same source. Combine the schema. We integrate the schema so that the metadata of the different sources is combined, and we will be able to identify the data as representative by a single schema. However, this kind of integration or generally data integration would produce problems such as entity identification problem, which means that identifying real-world entities from multiple data sources. So we will have two different tables representing the customer or the person who's purchasing, but they will have different names or they will have different attributes, although they will be containing probably the same data. So this will be a problem when we integrate data together. We are supposed to detect and resolve value conflicts. For instance, possible reasons for value conflicts is such as the usage of different representations of scales, such as metric and British units, or different representation of temperature, Fahrenheit and Celsius, and so forth. When we integrate data, the main problem that we face is redundancy, the fact that data will be repeated within the database. And this happens when we integrate multiple databases and we have the same attribute with different names in different databases. Other cases is that when we have an attribute that is derived from another attribute in another table. For instance, the age and the date of birth. Okay, so the age is actually derived from the date of birth. So this will be actually redundancy. And redundant data can be detected using correlation analysis. However, if we carefully integrate data, if we were mindful when we are integrating data, then this will reduce redundancy possibilities and inconsistencies and will improve our mining quality and speed. So this is an example of data integration. So we have customer and client. Customer is coming from source 1 and client coming from source 2. Customer will have an ID, name, street, city, and sex, and then these will have values. Client will have a client number, last name, first name, gender, address, phone or fax. Now these are these are data. However, we will have redundancy. So this is a customer's table showing the data integrated and cleaned. Okay, so we will have a new ID, a new number, and we will have the last name, first name. We do not need the name. We will have the gender. We will have the street, the city, the state, the zip, the phone, and fax. Each one of them separated. And we will have also the CID and the client number. However, we would have some missing data here, but it's not a problem because this is not existing in both tables. The third step of data in data preprocessing is data transformation. And data transformation includes smoothing, aggregation, generalization, normalization, attribute or feature construction, and discretization. discretization. Smoothing is about the removing of noise from data, and this can be different from, this is a second step of transformation, and we're going to see that in a minute. It's very similar to what we do in the cleaning, but in this step it is done for transformation purposes. We also have aggregation, which means that we want to summarize data in a form of a data cube construction. We also have generalization by the creation of concept hierarchy, and we will explain that. And we also have normalization, which means that we will scale data so that we will have it in specific range. We have minimum maximum normalization, we have z-score normalization, and we have normalization by decimal scaling. And we also have attribute feature construction, which means that we will actually have new attributes constructed from ones that we already have, and then we'll talk about discretization. Data transformation, basically normalization, means that we will be generating new values. So we will have a new minimum and a new maximum for our data. For our data. Let's go to the example because it will explain this formula. So for instance, we have values of the income of an employee ranging from $12,000 to $98,000. And we want to normalize this data to be between 0 and 1. Okay, so now this is the minimum, and this is the maximum, and this is the new minimum, and this is the new maximum. Now, if we want to normalize the income of an employee, which is $73,000, then we will be applying this formula. V, which means the value that we want to normalize, minus min A, which is the minimum, the minimum, which is 12,000, max A, which is the 98,000, minus min A, which is the 12,000, multiplied by new max, which is 0, minus new max, which is 1, minus new min, which is 0, plus new min, which is 0 in this case. However, these are multiplied after they are subtracted, they are multiplied by this value, and then they are added to the new min. So after calculating this, we will find that $73,000 is actually 0.716 using this formula. The second type of normalization is z-score normalization. In this case, we will be using the mean, mu, and the standard deviation. Example, we have the mean to be $54,000. The standard deviation is 16. In this case, then the value that we want to normalize is 73,600 minus, this is just the value, okay, 600 minus 54, which is the mean, divided by 16,000, which is the standard deviation, and the value is 1.225. Normalization by decimal scaling is actually dividing V by 10 to the power j, and we want to divide to the power j will depend on the value of V. So if V is between 0 and 10, dividing by 10, you will get a decimal number. But if the value is between 0 and 100, in this case, you'll have to divide it by 100 to get a decimal value. So we want the value to be less than 1. We want it to be a decimal value. That's how J is determined. Discretization, it means that we want to reduce the number of values for a given attribute, and this attribute is actually continuous, so the data is considered to be continuous. However, we want to reduce these values to be in form of intervals. An example for that is, instead of having age value of an attribute, we will have, or we will define, young, middle-aged, or senior. In this case, this is considered to be discretization. So we do not have numerical values, we will have labels instead of these numerical values for age. So for the three types of attributes, such as nominal, ordinal, and numerical values, discretization means we want to divide the range of these of the continuous value into of the continuous attribute into intervals, and we will have labels for that. And if you think about it, this sounds like the bins when the binning idea. However, we'll have names for each bins, and this is how we will actually divide or the range of attributes. So typical methods: binning, just as I mentioned, histogram analysis, we have cluster analysis, and we have decision tree analysis. So binning, we still have the same binning idea. So here we have equal width binning, and here we have equal frequency binning. So equal width binning, the bin will range or will have the width of 10. So this is actually from 0 to 10, and then from 10 to 20, and from 20 to 30. Okay, and this will contain the values that is between these ranges. Okay, so 0 and 4, and here 12, 16, 16, and 18, and here 24, 26, 28, and in this way we've created three bins. Here we want to have equal frequency, or as we called earlier, equal depth. For example, in this case it's 3. We will only have 3 values per bin: 0, 4, 12, 16, 16, 18, 24, 26, and 28. Concept hierarchy generation, which is a generalization method, is used to understand and organize concepts. Just the example that we just saw in address. So an address of a person can be divided into street address, zip code address, and city address, and country address. Okay, so when we use concept hierarchy, we actually either generalize the values or specialize the values. So we can either choose to only keep values per country, okay, and or we will have on country level, or we'll have the values on city level, or we'll have the values on zip code level, and this depends mainly on the data that we have. And concept hierarchy can be generated by warehouse designers and engineers, or it can be automatically generated. It doesn't have to be done manually. So as I said, it's either specification of partial or total ordering, which means that either it's generalization or specialization. So it's either that we go to the street level or to the country level or the state level, however we want. Okay, and we can this will allow us to group data based on relevance. For instance, Urbana, Champaign, and Chicago are all in the state of Illinois, I guess. Okay, so this way we are generalizing the data that we have all of them within. We will only state that all of them based on the state, or we will do that based on the city. Okay, and again this will depend mainly on the data. If the data are all for people who are all in the US, then having the country does not differentiate between the different objects. However, if they are from different countries, then having the country alone would be enough. Not having, we don't need to have the cities. So if you think about it, if we use the country, for instance, and the objects will be belonging to 15 distinct values. If we use the province, in this case, we'll have 365 distinct values. If we have the cities, in this case, we'll have 3,567 distinct values. If we use the street, we will have 600,000 distinct values. And this is actually depends on what kind of analysis are we applying. However, the levels will determine the different distinct values that we'll have. Now, the fourth step of data reduction, of data preprocessing is data reduction. And with data reduction, for instance, in a data warehouse, the data warehouse may include terabytes of data, which means that we will have complex data and the mining will take longer. And we're talking about days or probably weeks of processing before we will arrive to analysis, to results. So that's why we apply data reduction, and data reduction is applied to have reduced representation of data in terms of volume, but it will use or will produce the same or almost the same analytical results. So for data reduction, we have dimensionality reduction. These are the strategies to reduce data. Numerosity reduction and data compression. The dimensionality reduction, it means that we will be reducing the number of random values or attributes that we are considering. So the values that we have, we will be considering if they are relevant or irrelevant. If we have attributes that are not relevant, are not beneficial to the analysis, we will be removing them. So the purpose of dimensionality reduction is to select a minimum set of features, such as the probability distribution of different classes given the values for those features is as close as possible to the original distribution given the values of all features. So we want the minimum set of features, okay, that when we use them, we will have the same or the closest distribution of classes. Classes means different types of objects in the data set, okay, as if we are using all features. And for the dimensionality reduction, we have one of the methods is to apply heuristic methods. And heuristic methods is to use, because we have too many choices when we want to reduce the number of features, we have 4 approaches to apply dimensionality reduction. We can use stepwise forward selection or stepwise backward selection, or we can combine forward selection and backward selection, and we also can combine we can use decision tree induction. So step forward selection means that we first start with an empty set of attributes. We assume that we have no attributes in the list of attributes that we will use. And then we will be determining the best attribute to be added, so it will be producing a distribution that is similar to the original class distribution. And we keep adding attributes, okay, based on this condition that this attribute is going to be the best of the remaining original attributes. The stepwise backward elimination will assume that we have all the attributes, and then it will remove the worst attribute remaining in the set. Combining forward and forward selection and backward elimination is that when we first the stepwise forward selection, we will first at each step decide what is the best attribute to add and what is the worst attribute to remove. So we will be applying at each step both approaches. And the decision tree algorithm actually it is originally used for classification. However, it's also used for dimensionality reduction, and we're going to talk. I'll have an example about that in a minute. So this is an example for forward selection, backward elimination, and decision tree induction. So this is the initial attribute set. So for forward selection, we will start with an empty set, and then we add the best, and then we add the best from the remaining, and we continue until we have the reduced attribute set. The backward elimination, this is the set. We start by the whole set, and we start eliminating the worst until we finally arrive to the best set. The decision tree, we will actually be discussing each attribute. So we'll be looking at A4, yes or no. If yes, A1, yes or no. However, here, if it's no, A6, yes or no. And then we will have the reduced attribute set A1, A4, A6. So this is actually a general example with no details, but we will talk about the decision tree induction further when we talk about classification. If you notice here, we have classes 1, 2, and 1, 2, where class 1 is the selected attribute, and class 2 is the attribute that was not selected. So I will stop here for this week, and next week, inshallah, we're going to continue with data pre-processing, and we will continue from the data compression topic, inshallah. Thank you very much. Assalamu alaikum.